Welcome to a lesson with Dr. Powell. Let's take a look at the Teichmuller character that goes from z, pz, the cross, so the units here, and it goes to the p-adics cross, so the units here, okay? Maybe we'll use an omega here to denote this character. And suppose that we have, so we take x in here, and this is the way we're going to define it. Let's just take a lift of x to zp, so mod zp, it's going to be the same thing as x over here. So we take a lift of that. So when I write this down, think of it as a lift. Think of it as, pretty much any lift in there. Make it simple here, and it'll work great. So we're going to take, so what we're going to do is we're going to take a limit as n goes to infinity of x to the p to the n. Okay, now this will define this character. In fact, it'll be a group homomorphism, multiplicative homomorphism here. And one way to see that, assuming this limit exists, which we'll talk about. So if we assume this limit exists, then using the fact that multiplication is continuous, according to the p-adic metric here, with the, okay, then what we end up getting is we can write this. We could think a times b, p to the n, and then we could think of p to the n, let's see, distribute that over here, p to the n, and since it's continuous, then we can split the limit across to the different parts of the multiplication, assuming continuity right here. And then what we end up getting is we see that this is multiplicative, just as expected. Okay, so that's an essential characteristic of this. Isn't just a map here from here to here. It's not just a lifting, a set map, but it's more than that. It's a homomorphism. Okay, so it's based upon, and we get this homomorphism property based upon this limit right here existing with the p-adic topology here. So let's discuss briefly how this limit exists and what it is. First of all, let's consider z p to the n z, and look at the units right here. What are the units in here? And how many are there? Well, if we think of the Euler phi function of p to the n, so to kind of think of the size of this, we get p to the n minus p to the n minus 1. Okay, so we're going to use that idea because we know if we take anything in here and raise it to that power, we're going to get 1 in this mod. So in particular, if you take some x in there and raise it to the p to the n minus p to the n minus 1, that's going to be congruent to 1 mod p to the n. Okay, so this is the same thing. So that's actually the same thing as saying x by multiplying both sides of that congruence by x to the p to the n minus 1. X to the p to the n is actually congruent to x to the p to the n minus 1 mod p to the n. What does that mean? That means that the difference of this and this is actually 0 mod p to the n. So so p-adically we're getting small, we're fairly small, we're within p to the n, and as n increases we're again smaller and smaller, which means that this is a Cauchy sequence and has a limit. So therefore we've shown that the limit exists, all based on the Euler phi function. So we have this limit exists, and it provides us a character. It's multiplicative, which takes us from here into here. And we also know in particular that that this is injective, that omega is injective. Now, how do we know that? Well, we know, well, if we look this limit right here, at least in taking that limit, let's think about that for a minute. X to the p minus, let's think about x to the p minus x. So we can rewrite this as x to the p minus 1 minus 1 times x. And we think about solutions of this mod p. In particular, we look at this right here. I mean, it's separable. We can use Hensel's lemma. There's a unique solution that extends something to something else. So in particular, let's suppose that you have a solution in here. In fact, everything in here would be a solution. This splits linearly everything and gives us a linear factor here. Like if a is in here, then x minus a is going to be a factor. That's a solution. So we can kind of think about Hensel's lemma, because that'll extend up to a unique solution in ZP. A solution here, if we have it, a solution in ZPZ cross, then it'll extend up. And okay, and that's great. And let's take a look at this in particular, because when we take this limit, then, and we even take the limit, right, of this, let's just take the limit of this expression here, assuming, with this limit existing. Now, if you take the limit of this expression, the limit will split across the subtraction. The limit of x to the p and the limit of x will actually be the same when we throw a p to the n up there and take a limit. Because it'll just be powers of p, and going off to infinity in both cases, we'll get 0. And then with, and so we'll end up getting 0. And notice that we can also put the limit inside right here and keep it right here, which means that we're pretty much looking at this fact that omega of x raised to the p minus omega of x, that's actually going to be equal to 0. So that we get actually that that this Teichmuller character is this root of this polynomial. It's actually the lift that we want. And the lifts, by uniqueness of lift, we actually get injectivity for omega. So for this Teichmuller character. So we have an injective character with kernel just 1. And that's an homomorphism and is well defined. Thanks for watching.